Assalamualaikum warahmatullahi taala wabarakatuh. Salam sejahtera. Today we will continue on our lesson, which is heat conduction in cylinders and spheres. So if you look at the part 1, we have learned on heat conduction on a plane wall. Okay, on a plane wall. Now we are go in very superficially on the conduction in cylinders and spheres. Okay, so still in this topic we will only cover on the steady heat transfer through the pipe can be modeled as a steady and one dimensional. So we are only assessing ataupun discussing on a steady problem and one dimensional problem. We're not going to study on unsteady and multi-dimensional problem. We only cover on steady and one dimensional. So for cylinders and spheres, there's no L anymore in the formulas. So the direction of heat transfer through the radial direction all can be expressed in T equal to T in term of R. Okay, the temperature is independent of the azimuthal angle or the axial distance. The situation is approximated in practice in long cylindrical pipe and spherical container. It is actually only approximated practice. So if you calculate something and you get not similar to the actual situation, it is understand that your calculation is only approximated calculation. You can't get the exact value of what you experimenting as compared to what you try to prove using analytic. Okay, what you calculate is only approximate value only. You can't get the exact value. So this is for cylinder cases is actually to translate that the heat loss from hot water pipe or cool water pipe to the outside in the radial direction, and thus the heat transfer from a long pipe is one dimensional, which means the transfer rate, the heat transfer that we are considering only on the radial direction, not on the length of the pipe direction. Okay, on the radial direction. Of course, if you try to transfer heat, for example, you have a long pipe. Where's my this is your pen. Okay, for example, you have a pipe here. I'm sketching a pipe here. You try to transfer some liquid or fluid which is temperature initially as 100 degree Celsius. Then the outside of the temperature probably you only get 80 degrees Celsius. So this is also heat transfer. There's heat transfer occur along this along this one cylindrical pipe. Okay, heat transfer from inner to the outside of the pipe. So what we are trying to learn today is only the direction of radial direction. This is also occur some heat transfer, but what we are measuring today is only on the radial direction, which is from the inner of your pipe to the outside of your pipe. Okay, please remember that we're not measuring from inlet of the pipe to the outlet of the pipe, the heat transfer there. Of course they're the same. Of course there is some heat transfer occur from inlet to the outlet, but that's different formula. Okay, that is different formula, but we are dealing with radial direction. So today we will only cover on the radial direction. We will not covering to the for example this one on the longitudinal axis. Okay, we only cover on the radial direction. So the formula itself is only cover for R here, R cylindrical, right? R cylindrical here. We are still harnessing the thermal resistance formula, where we try hardly to make all the heat transfer formula into this form, into this kind of form, where Q equal to T1 minus T2 divided by R. Okay, it is either convection or conduction or radiation. We try hardly to make all the form of heat transfer equation into this kind of form. This kind of form we call it as a thermal resistant theory. Okay, thermal resistant theory where for R conduction is different, R radiation is different, R convection is different. And now we are learning on R cylindrical, where R cylindrical is depend on radius 2 divided by radius 1. This is radius 2, which is outer radius here, outer radius, divided by R1, which is the inner radius, and we normal logarithmic those ratio and divided by 2 pi times L. L is the length of your pipe, and K is the material properties of your pipe itself, the thermal conductivity. Then you can get R cylindrical there, R cylindrical. So this is specifically for conduction, R cylindrical for conduction. Okay, conduction resistance. How about spherical? For spherical, we are using this formula, R2 minus R1, where R2 is outer radius and R1 is the inner radius, divided by 4 pi R1 times R2 times K. K is the properties of material of that spherical shape. Okay, for example, this is your spherical shape, so the K itself is the thermal conductivity of that material, of that shape. Okay, so there's no normal logarithmic for spherical equation. Okay, we remember that this is only for conduction, and for cylindrical itself is also for conduction. So how about the convection for cylindrical? So it lies the same. The only difference between plain wall and cylindrical is depend on the conduction. For the convection, it is still the same formula that we learned as before. Okay, R convection is equal to 2 pi R. R convection equal to 1 divided by 2 pi L kan. Yang last one is L kan. L darab H. So in this case we have R, so we put it as a R here. Right? You get it there? So for spherical, it is different. 4 pi R squared times H. Last time this is A, right? For convection, R convection from basic formula is 1 over A times H. A is surface area. Surface area. For surface area of a cylindrical, we use this one, 2 pi RL. How about this one? This one is for the outside. Spherical, kalau cylindrical, outside. Surface area, outside. Kalau this one is surface area of spherical. Spherical surface area is 4 pi R, right? 4 pi R squared. So the only difference from all resistance theorem is on conduction part. This is conduction part, and this is also conduction part. The rest is similar. This is A actually, surface area. This is actually surface area. This is also surface area. This is also surface area. Okay, if you are familiarized with the surface area of any shape, basically only formula for convection you need to memorize is only this 1 divided by surface area times H. Alright, hope that you're clear with that. How about we have a multi-layer cylinder and sphere? So it comes easy if you use a thermal resistant network. Kan? If you have inside pipe, here we have some convection, and the pipe itself has multiple layer. So the first layer is the first resistance, second layer is the second resistance. So the third one is almost usually apply on the penebat, some kind of penebat insulator, and the last one here is on convection lah. Another convection happen. So it is become much more easier if you use a thermal resistant network. So you need only to find the R total of all this, then apply with this main formula, then you can get heat transfer rate of any problem regarding on cylinders or spheres. So you can take a look at this slide how they are trying to make it complex of all the resistance, thermal resistance there, but I don't suggest that you memorize all this one. You only need to memorize every single of R resistance. For example, here the resistance of cylindrical, what is R there, the conduction, for conduction. Just memorize one particular, don't memorize the whole this equation. This is just waste of time, which mean also if you memorize this formula, you not understand a basic concept of heat transfer itself. If you try to memorize all this long formula, you should memorize how the problem is tried to convey and how the problem is try uh, to pronounce, and from that you can solve from any problem, any kind of problem. Okay, from basic, you try to understand from basic, then try to form that kind of formula, then try to solve it for Q. Okay, furthermore, we have critical radius. For example, usually pipe, we add insulator at around the pipe to prevent the pipe itself having some extreme heat transfer. What does it mean that extreme heat transfer? For example, you have for example that I show you in the previous example, where you have a long pipe, where inlet temperature is 100 degree and the outlet temperature, you try to maintain that temperature for at least you get 98 degrees Celsius. So how to prevent that that pipe have extremely heat transfer rate? So we add, ataupun engineer always add insulator ataupun insulation lah kat sini. Kalau you nampak dekat you nampak dekat air conditioner kan, sebenarnya dia black pipe kan, dia ada macam black pipe kan, you nampak dia macam black pipe kan, sebenarnya dia adalah insulator. Sebenarnya black pipe, black tu dalam dia ada copper pipe tu yang bring your punya bring you punya cool fluid tu, fluid yang apa dipanggil, kadang-kadang ada R134A, ada yang R12 type yang you dah belajar dekat thermodynamic tu, dia punya jenis-jenis fluid yang ditransfer tu. So in order to maintain that temperature in ataupun to prevent extreme heat transfer in your pipe, so engineer always apply insulation dekat cylindrical pipe. So how thick is your insulation required to transfer from one location to another location without losing a lot of temperature to the environment? Okay, kalau boiler, for example, boiler kan, you nak transfer fluid dalam bentuk panas kan. Contoh boiler awak di tingkat bawah, you berada di tingkat 11, you nak pakai air panas dekat bilik air. So nak transfer dia pergi ke atas tu, dia boleh hilang kepanasan dia tu. Daripada, for example, you nak transfer 100 degree Celsius, you nak sampai shower dekat kepala you 100 degree Celsius. So you perlukan insulator. So berapa tebal insulator tu yang perlu dikira, yang perlu diconsider untuk sepanjang, kalau rumah awak berada 10 tingkat tinggi dia, so berapa insulator tebal dia yang diperlukan. From that we will study on some critical radius of insulation. Okay, critical radius of insulation. How thick of the insulation required to transfer ataupun to minimally reduce ataupun decrease heat transfer, since adding more insulation to a wall or to the attic always decrease heat transfer, since the heat transfer area is constant. Okay, so adding insulator will increase the thermal resistance. So there are special formula to calculate that how many thickness that require of your insulation, which is R critical. We always set that R critical for the insulation. For example, this is your insulation. So what is the R critical? R critical, which mean what is the maximum of thickness required before the convection happen is reduced around the cylinder. For example, you can imagine that this is your cross sectional of your cylinder ataupun cross sectional of your pipe tu, pipe bentuk cylinder kan. Kemudian this is your kejap saya tukar ni kepada laser point ataupun pen. This is your pipe. This is your pipe here, and this is your insulator. Okay, insulator. Nampak sini dia ada radius, inner radius, ada outer radius. Sini ada, kita lihat dekat graph ni ada inner radius, ada outer radius. Boleh lihat kat sini dia ada critical radius. Di mana letaknya critical radius ni? Di tengah-tengah sini. Di tengah-tengah sini. Dia berada di tengah-tengah sini. If you try, for example, kalau you dilantik sebagai seorang engineer, you nak transfer some fluid with 120 degrees Celsius to another place with long distance. So the critical insulator you need to apply is based on R critical here. You need to have more than this R critical thickness. Kalau you punya thickness di sini untuk pipe ialah sebanyak setengah inci, radius dia setengah inci, ataupun full diameter dia ialah 1 inci. Diameter untuk awak punya pipe 1 inci. So berapa critical radius yang diperlukan untuk awak punya insulator? Adakah sebanyak 1 inci lagi? So the total you have di sini dan di sini ialah 2 inci. Adakah begitu? So how to calculate that? So that you boleh transfer fluid from one location to another location without suffering lot more losses to environment, lot more heat losses to environment. So to find that R critical is just by dividing the K of your metal ataupun your insulator material divide by H, thermal conductivity of convection of the outside. Kalau thermal conductivity untuk environment yang sejuk berbeza dengan berbanding dengan panas. Kalau di compare secara reality, H thermal conductivity untuk negara sejuk seperti Korea, UK, US, negara sejuk lah ni, dengan H thermal conductivity dekat Malaysia berbeza lah. So K it is constant, which is properties of you punya insulator. Ni properties of you punya insulator di sini. Tapi H is depend on environment, temperature environment. Untuk sphere berbeza. We are using 2K divided by H. Okay. So that is the application of thermal resistant. Kalau you nak beli ataupun you nak transfer ataupun you nak gunakan insulator dekat air conditioner, so you have a basic formula here. What kind of insulator you nak guna dan berapa tebal you nak guna dan berapa panjang dia you nak maintain dia punya temperature tu. So this is the basic formula. You tahu thermal conductivity untuk insulator tu, kemudian you check dekat properties table of thermal convection untuk environment awak, dia punya H tu. So you divide kan, you boleh dapat R critical untuk you punya insulator. So you boleh apply di situ. For example here, K max insulator ialah 0.05 watt per meter degree Celsius divided by H minimum. So lebih kurang 1 cm R critical yang diperlukan untuk transfer hot water. You imagine lah, 1 cm tu apa? 1 cm ialah from inner here to the, from core to the outside ataupun center sini. Minimum you kena ada 1 cm jarak dia. Okey, bukannya di luar sini 1 cm, tapi dia harus di tengah-tengah 1 cm. Alright. Then we go to some example. Here, for example, we have heat transfer to a spherical container. For example, we have a spherical container where the internal diameter spherical tank is 3 meter. Uh, 3 meter tank made of 2 cm thickness stainless steel, was K is 15 watt per meter Kelvin, is used to store ice water, which is T inner 0 degrees Celsius, and the tank is located in a room whose temperature is T environment 22 degrees Celsius. The wall of the room are also at 22 degrees Celsius. Dia cakap wall dia 22 degrees Celsius. Okay, given H inner 80 degree, sorry, H 80 watt meter square K, and outside 10 watt meter square K. Calculate the rate of heat transfer to the ice water in the tank and the amount of ice melt during 24-hour period. Okay, dia cakap be realistic with natural convection from the outside and the radiation from the outside, which mean ada radiation lah dekat luar sini. Seperti begini, radiation. Remember what we learned before? If radiation occur in your problem, in your topic, the radiation is actually in parallel with your convection. Okay, the radiation is in parallel with your convection resistance. Dia tak boleh kira dia series. Kalau you kira dia series, salah. Apa maksud kira series? For example, this is resistance for inner side kat dalam. This is resistance for your pipe here ataupun spherical, and this is your convection happen at the outside, and this is radiation happen at the outside. If you put your thermal resistance just like this, whereas this is your R red and this is your RO, this is your R1 and this is your RI. You made a big mistake. Okay, you made a big mistake. This because R red and RO, it is in parallel, which is just like this. So you need to solve them as a parallel radiate. Parallel resistance. So to solve that, you need to use T infinity 1 minus T infinity 2 divided by R total. Right? So R total equal to equal to R convection of inner plus R conduction for spherical tank. We put it as R1 plus R for this, which is R equivalent. R equivalent QIV. Okay, so R EQIV macam parallel punya resistance lah. You kena solvekan dia by 1 divided by R EQIV per 1 R red plus 1 RO. You pusing-pusingkan dia sama dengan RO R red plus R red RO, kan? Kalau you pusing-pusingkan dia, so this whole lot, alamak, this whole lot must be replaced in this, barulah you boleh dapat. And that is for A. And for B, the amount of ice melt during 24 hours. You can solve that. You can solve that by knowing the final equation of this. No, the final Q, not final equation. Bila dapat Q nanti, kemudian you solvekan dia menggunakan melting ice sama dengan Q by H H untuk ice tu lah. Berapa? Selalunya yang ini you boleh dapat dekat properties table, dekat HF. Kalau you ingat lagi dekat thermodynamic, you boleh dapatkan HF tu dekat properties table. Berapa? Q divided by HF, you boleh dapat direct. Which Q? This Q. Okay, which Q is this Q? So your task here today, you have a task today, which is your quiz number 2. Quiz number 2. You need to solve this one. I will give you a proper paper ataupun a proper quiz 2 in separated from this slide, in the separated paper ataupun in separated task. You need to answer that, and you need to upload your works. Actually this this is your tak boleh lah jadikan you punya latihan saja, sebab this is this question I took from example 3.7. This is example 3.7. Example 3-7. Look at that example. Try to solve that this problem, and I will give you another question based on cylindrical and spherical problem, so that you need to answer that quiz and upload everything in the e-learning. Go get that the quiz in the e-learning and answer in the piece of paper. take a picture in a PDF form and upload it in e-learning too, right? Okay, and that is for your this example is for your study on learning, and that example will help you how to solve a quiz, which is I will upload it later on in the e-learning. And for heat transfer from fin surface, we will cover on heat exchanger topic. So we will skip this subtopic. We will skip this subtopic. Don't worry. We will study deeper, breather than this topic in the heat exchanger topic, right? So that's it for today. Thank you. Remember that this is your example to make you familiar with cylindrical and spherical problem. Do it yourself. Try to understand yourself. I will give a quiz, so you will answer it and upload it in e-learning. Okay, thank you again. Assalamualaikum warahmatullahi taala wabarakatuh.